Hello folks, this is the question of 2018 May-June paper 42 and the question number is 9. It says that first it asks us state what is meant by the magnetic flux linkage of a coil. So it's actually the magnetic field that passes through the whole cross section of a coil, and it is expressed as the product of phi is equal to the magnetic flux density into the area of the coil into the number of turns in the coil into cosine of the angle between let us say this angle is alpha here. The angle alpha is somewhat like this. If this is the north pole of the magnet, if this is the south pole of the magnet, if this is the breadth of the coil, and if we have this is the one of the flux lines, one of the field lines here, so if I draw a normal here, normal like this, so this alpha is this angle, so alpha is the angle between the magnetic field line and the normal to the coil. So, or it is also expressed as somewhat like this. So it is BAN sine of say, let us say sine of theta, where theta is this angle. So in both way the situation is same. It is actually the value of both of them will be same. Now in question number B we are asked a coil of wire has 160 turns, so our N is equal to 160 here, and diameter 2.4 centimeter, so D equal to 2.4 centimeter. In meters it will be equal to 0.024 meters. The coil is situated in a uniform magnetic field of flux density 7.5 millitesla, so this B is equal to 7.5 millitesla, which means it is 0.0075 Tesla. This 7 should be at the third place after decimal. As shown in figure 9.1, the direction of the magnetic field is along the axis of the coil. So this is the axis of the coil, and the direction also in this direction. The magnetic flux density is reduced to 0 in a time of 0.15 seconds. So this is small t is equal to 0.15 second, and we have the magnetic field density reduced to 0. So that means the final, so this B final is equal to 0. Now what it says is, show that the average EMF induced in the coil is 3.6 millivolts. So now we have this phi should be equal to this E should be equal to phi 2 minus phi 1 by this time, and this phi 2 is the final amount of flux. This phi 1 is equal to the initial, so it's equal to since the flux density has been reduced to 0, so this phi 2 should be equal to 0, and let us see minus, and also here minus it will be BAN, so it should be equal to BAN whole by T equal to BAN by T, and that's equal to so B is simply 0.0075 into A is pi into D square 0.024 square into N is 160, so we have a pi by 4 remaining here, 4 into this time is 0.15. So the value it will give will be, so let me use calculator here from another mobile. So let me use the calculator. So its value will be equal to 0.0075 into shift to pi into 0.024 square into 160 divided 4 equal to divided 0.15 equal to, so it's equal to what it gives is 0.003619 volt, and that is nearly equal to 3.6 millivolt, which is the required answer here. So now what it says is the magnetic flux density B in the coil is now varied with time t as shown. So it remains constant for some time, it decreases uniformly, again constant at 0 for some time, again decreases uniformly but at a higher rate, and again given constant. So from here we have to draw the graph for the variation of EMF. So let's remember that this EMF is equal to, again it's the same thing here. Here B is constant, so B is constant means the flux is constant, and if a flux is constant, so this E is equal to phi 2 minus phi 1 by T, and this is minus. So if the flux is constant, E should be equal to this quantity will be 0 and E should be 0. So that means E will be 0 at several places here. So what happens is, from here to here E should be 0, E should be 0, from here to here 0 0 0 0 0 like this. Again from here to here E should be 0, E should be 0 because he is constant here B. Again from here, so somewhere down here we must have E should be 0, so it is 0.4 1 2 and somewhere here. So from here again E should be 0 0 0 0 0 0 0 0 0 till this voltage E should be 0. Now here the value is, as we have already done it here, so we have 0.15 seconds from here to here, it is 0.15 second. The flux density was changed from something to 0, and the EMF was 3.6 millivolt, 3.6 millivolt. So the EMF here is 3.6 millivolt. So from here this is 2, this should be 3, 3.2, so 3.6 here, so this should be 3.6, so 3.6 till here, till here should be 3.6, 3.6 6 6 6 6 6 6 6 like this, from here to here. So from here to here it should be 3.6 volts. So there's a drastic jump here, and there is again jump here. Now in the second case what we have is, we have the same change of B, but the time taken is half. So here it is from here to here 1.5 second, but from here to here it is 0.75 seconds. So 0.75 second means that now time is half. So since time is half, E should be double. It should be double of what we just did it here, 3.6. So its double is 7.2. So its value should be equal to, this is 6. This should be 7.2. So the value should be from here to here 7.2222222 till here. It should be 7.2. So it should jump like this. It has jumped like this, like this, like this, like this, like this, like this, and again jump back somewhat like this, jump back somewhat like this. Now from here it again becomes 0. So this is the pattern of the EMF in the coil.